So, good morning, welcome. This is AP Stats. The AP test coming up is, well, AP week starts May 6th. So the first week is a lot of stuff that does not involve statistics. It turns out the stats test is the second week. And pull that up. So week 2, stats is on Thursday of the second week. It's in the afternoon. It's an afternoon test. So May 16th is what we're shooting for. So we're about 6 weeks out. 6 weeks from the AP test. We have one weekend review. Typically what we do is we make it a Saturday from noon to 4 is what we ask students to mark out. No, you might have, if you have Saturday work, you have some time to get that straightened out. I'm thinking that we could meet the weekend between May 4th. Let's see if that would work. That's the week after Easter. Create an account. No. All right, so it's, you know what? We're going to have to meet May 11th. May 11th is what I'd like you to schedule for our weekend review. We're doing an actual AP test and the multiple choice portion, and you get it graded. So, and we get to go over the ones you missed. So it'll be like an actual AP experience right there on Saturday, May 11th. So take out your calendars and set up noon to 4. For AP Stats review. Looks like I'm probably going to be doing an AP Calculus review that day also in the morning. Some of you are in my AP Stats. So it's just going to be AP review on Saturday, May 11th. Clear your calendar now. And please raise your hand if you're thinking that there is a possibility that you'll be able to show up on Saturday, May 11th from noon to 4. That's awesome. I'm seeing lots and lots of raised hands. I look forward to that. It's usually the richest review experience of the entire course. So plan to be there. So as we launch into this last leg of AP Stats, please pray with me, and then we're going to continue. Father God, we do thank you for this opportunity to learn about truth that you've revealed. Thank you for giving us the capacity to engage in the scientific method and to be able to read the book of creation that you wrote, the other book that you wrote. Pray that you would give us clarity and focus, good health as we prepare for the AP test these next 6 weeks. For it's in Jesus' name I pray. All right, we're going to pick up where we left off on, and I'll put a little review in there. So for those of you who were absent or just forgot a lot of stuff that we're working with, take out this handout, part 3 of it. There's a lot of overlap between test and intervals part 2 of 3 and test and intervals part 3 of 3. So even those of you who have not yet watched the video, this will be helpful for you. Now, I think we use some other numbers here. I would like you to, for practice, since we did not fill in a lot of this sheet on part 3 of 3, I'd like you to try an additional example to kind of review what we did. We're looking at type 1 and type 2 errors. And in case you forgot, the probability of a type 1 error, or a type 1 error is a probability. So type 1 error is when you incorrectly reject the null hypothesis. It's also alpha, so the height of the limbo bar is numerically also the probability of a type 1 error. and the probability of incorrectly failing to reject the null hypothesis is beta, also called the type 2 error. We use the OJ video, OJ Simpson, to illustrate how the people who were upset by the ruling in the OJ Simpson case were concerned that, first of all, the jury had failed to reject the null hypothesis. The null hypothesis was that OJ was not guilty. They failed to reject that. So they pronounced him not guilty. People who were upset about that thought that that was an incorrect ruling. So the people who were upset were concerned that a type 2 error had occurred. Now, instead of the 4 numbers that we had on that day, I'd like you to try this example again, but this time with new numbers. Use 10 who are actually guilty were declared guilty, 2 who were actually not guilty but declared guilty by the jury, 5 people were actually guilty but declared not guilty, 7 were actually not guilty and declared not guilty. So using those numbers to get a fresh start on this, what would be verbally understood and numerically understood the probability of a type 1 error? So try to calculate the probability of a type 1 error based on these new numbers. Just going to pause the camera while you calculate that. Okay, camera's back on. Now, what it means by a verbal representation of a type 1 error, in this case, that would be what's the probability of a type 1 error, in this case would be a guilty verdict, given that the person is actually not guilty. How are we supposed to arrive at that? Well, remember, if you're thinking that a type 1 error is incorrectly rejecting the null hypothesis, then what our observation is, this is the eyeball term right here. Oops, okay. So what we observe is a guilty verdict. They rejected the null hypothesis is what we observe. But since it's incorrectly done, we're saying that given the reality that the person is actually not guilty. Now, I've got 2/9. Raise your hand if you came up with 2/9 when you did it. Okay, so that's the probability of a type 1 error. That's alpha. That's actually where the limbo bar is set. Try number 2. See if you can calculate and express it verbally. Number 2 is the explanation of a type 1 error in the context of the problem. Okay, so since this is going to feel like new material for you, I'm going to talk you through it. Now remember, a type 1 error occurs when we conclude that there is sufficient evidence that O.J. Simpson is guilty, when in reality, he's not guilty. So this is a concept that we actually did talk about before spring break. In the context of the problem, a type 1 error occurs when we send the innocent to prison. You don't need to write down all of these things. These are just thoughts that go into the answer. The actual explanation in the context of the problem would be this text in red. A type 1 error occurs when we send the innocent to prison. Any questions on problems 1 or 2? So this is review. No new concepts here. So try number 3 on your own, please. All right, we're back. So as we talk through number 3, forefront in our minds should be a verbal statement of the null and alternate hypothesis. So the null hypothesis is that the accused is not guilty. Just want to write it down here because that should be forefront in our minds is not guilty. Alternate hypothesis is that the accused is guilty. So, problem 3, where we're asking for a verbal and numeric representation of the probability of a type 2 error. since type 2 is incorrectly failing to reject, we have failed to reject it. So what we observed is a not guilty verdict. So what's the probability that we observe a not guilty verdict from this jury, given that she's actually guilty? So that's how we express the probability of a type 2 error. Verbally, numerically, we shrink the universe down using the heat gun to the actually not guilty portion. So turn on the heat gun and shrink this two-way table down to those 15 people. The actually guilty. So the probability of not guilty given actually guilty is 5 out of 15, or 1/3. To explain that verbally, that would be setting the guilty person free. So number 4, you should feel that that's review. So we talked about that Friday before break. Any questions on 1 through 4? Yeah, Lewis.
Like I see that type 1 error is the probability of incorrectly rejecting null hypothesis. But I don't see why type 2 error is the probability of incorrectly fail to reject.
Okay, so the question is, why is a type 2 error incorrectly failing to reject the null hypothesis? And that's by definition. It's not arrived at through reason.
Okay.
It is a definition. And so
it's just a concept.
It's a definition. That's how type 2 is defined. Type 2 error. So just got to know both definitions, type 1 and type 2. All right, so let's go on to number 5, which states, what's the power of the test? Yeah. Basically, the concept of power is how effective, it's basically what's the probability of correctly rejecting the null hypothesis. That's the verbal definition. It's like, how good is this judge and jury system at sending guilty people to prison? That's an example of correctly rejecting the null hypothesis. That's what power is. And so the power of the test is always 1 minus beta. So numerically, and you remember seeing these 2 pictures, which I think is the easiest way to process alpha, beta, and power. Here with the probability of the proportion of dogs who bite people, if they assume it's 25% and it's really 35%, then you put a vertical bar here that can move back and forth. Here you see alpha. As alpha gets smaller, beta gets bigger. And power numerically is always 1 minus beta. So once you find your type 2 error, and we calculated the type 2 error at 1/3, so power is going to be 1 minus 1/3 or 2/3. Which we did not spend any time before spring break calculating power, so this is, you're going to experience this as new material. Power, 1 minus beta is 1 minus 1/3 or 2/3. So the power of this test is the 2/3. It's the probability of correctly or sending guilty people to prison. So there's your first example of calculating power. The interpretation is that the probability that a guilty person will be convicted is 1 minus 1/3 or 2/3. So the probability of correctly rejecting the null hypothesis, or correctly rejecting the hypothesis that a person is presumed innocent, is 2/3. That's the null hypothesis. It looks like when I wrote up this handout, I decided to replace the phrase null hypothesis with hypothesis that the person is presumed innocent. That's just another longer way of saying null hypothesis. Okay, any questions on this opening activity here, just designed to review some of the basics from our previous lesson? Now, if I recall correctly, we did actually jump into some of the other pages on this particular handout. And let's take a peek. It might still be here. Did we do problem 25?
No.
Before break?
We did like A.
Part A.
We did part A. Okay, so let's just jump back into problem 25. Where we have a company is being sued for job discrimination because only 19% of the newly hired candidates were minorities when 27% of all applicants were minorities. Okay? So is this strong evidence that the company's hiring practices are discriminatory? Whenever I encounter problems like this on a practice AP test, I want to write down the null and alternate hypothesis. Try to do that. If you haven't already, try to write off in the margin what's the null hypothesis, what's the alternate hypothesis. I'm going to pause to let you do that. So, camera's back on. I noticed that some of you wrote null hypothesis P is equal to 0.19. And can someone tell me why it's not enough to say P is equal to 0.19 for the null hypothesis? What's missing in that null hypothesis statement?
Proportion.
Think spherical chickens. We had the spherical chicken talk, didn't we?
Nope. No.
Really?
Yes, really.
We did?
No. Sorry, I didn't mean to be confusing.
That's okay. So, yeah, there's one where I showed the pictures of my dogs observing things.
No.
You're kidding me.
No, you're not.
Do you want the brief version of the spherical chicken talk?
Absolutely not. We want the full extended version with bonus clips.
I'll tell you what, based on where we're at today, I'll try to give you an appropriate duration on the spherical chicken talk. Friends, there's a fundamental difference between humans and animals that shows up in math classes. There's a lot of articles out there where people talk about how, animals can do everything people can do. There's the difference between animals and people is not a difference in kind, it's just a difference in degree. We're basically animals, and that's a message that, have you noticed that a lot of people want you to believe that you're just really animals that are a little bit advanced, but there's really not much difference. Just a difference in degree. One thing that kind of bothers me in math classes is when the main verb is do. If you see this, do that. Have you ever been in a math class where they say, okay, when you see this equation, do these things, and then we'll give you a Jolly Rancher as a reward? Has that ever happened to you? It's like, don't really worry too much about understanding what anything means. If you see this, do that, you get a Jolly Rancher, otherwise you get some sort of punishment. Like they'll put, little electrodes up on your brain and give you like a shock.
Oh. Certainly not.
Shock therapy. This happens commonly in math classes. So, actually, that is how you train animals, is you train them with stimulus response training. People should be doing math differently than animals because symbols, like for example, P, should have meaning attached to it. Animals actually attach meaning to symbols using their senses. Like if I were to go to my dogs, Bonnie and Clyde, and if I want to teach them what a sphere is, I can just say sphere. If I want them to hear, basically, if I want them to have a sphere come into their imagination when I say the word sphere, I can put something spherical out there, like maybe a soccer ball. Say sphere, sphere, sphere. I know they attach meaning with their senses because when I say walk, they get all excited. because they know what a walk looks like and smells like and tastes like. So if I take out a sphere, they'll look at it, they'll lick it, they'll sniff it. So that even when I have the soccer ball behind my back, if I say sphere, it will come into their imagination. If I want to teach my dogs what a chicken is, I can bring out a chicken, let them sniff it, look at it, taste it. So that when I say chicken, they're going to get excited. It'll come into their imagination. But do you know why my dogs will never be able to imagine a spherical chicken?
Because they don't exist.
Yeah, they don't exist in the physical realm. They cannot be sensed. A spherical chicken, we're talking about an actual chicken that's perfectly spherical. You can cook it up on the grill, barbecue sauce, oh, they taste delicious. But they don't exist, so dogs can never sense them. Do you know why you know what a spherical chicken is?
Because we have imagination.
Yeah, well, dogs have imaginations also, but it's how you attach meaning to symbols. You can attach meaning to symbols with words. You can say a spherical chicken is a chicken that is spherical. And by just writing down that let statement, by pronouncing that let statement, you're attaching meaning to symbols with words. Something that no animal can do. Animals attach meaning to symbols, but they do it with their senses. You do it with your senses and with your words. Every symbol in mathematics should have meaning attached to it. And this symbol has no meaning attached to it. So exercise your uniquely human ability to attach meaning to symbols with words by attaching meaning to whatever symbol that you use in your null hypothesis. Kennedy.
Do you still have the spherical chicken in your drawer?
The question is, do I still have a spherical chicken in my drawer? Well, if I did, then it would be a physical entity that we could look at and sense. So, yeah, okay. Now, Kennedy wants to spice up the video a little bit.
Oh my God.
Now, friends, I'm not a spherical chicken, but this is my spherical chicken hat. Oh, it's on sideways. That's not even right. So, if spherical chickens did exist in the physical realm, they may look something like this, or like this. So, now, who made this? A student of mine named Mackenzie made this because she realized when she came to class on Spherical Chicken Day, and she made the poster in the back. But she realized, oh, okay, I've been lied to. I've been told my whole life, you're just an animal, you evolved from rocks and mud. And she found out that she has a uniquely human ability to attach meaning to symbols with words. She found out she's a human being. And she celebrated her distinctiveness by making that poster, these hats, for me and my children. This is a spherical chicken stuffed animal toy. It's mine, you can't have it.
How much?
Kennedy, have I answered your question?
Yes, you have.
How much would you sell it for?
Not for sale.
$2 million.
I won't take it. So friends, on the AP test, I don't know if you're aware of this, but
That's cool.
in calculus, for example, page 1, the very first thing they do on the exam is they tell you what the variable represents. Just example number 1. Unless otherwise specified, the domain of a function f is assumed to be the set of real numbers x. So x represents a real number. If you don't know that, you have no idea what the symbols represent, and you really can't do math responsibly unless the symbols have meaning. So, was all of that just to say that we have to, yeah, it is. You can't just go write P, you have to say,
the proportion of minorities that were hired.
oh my goodness. Let P represent the proportion of minorities hired. Okay. Yeah. So alternate hypothesis P wouldn't be greater than, it'd be less than 0.19, less than 0.19. Now, yeah, so that's one way to approach this problem, is to say that, well, in general, we hire, yeah, there's actually something strange about this. Let's assume because only 19% of the newly hired candidates were minorities, when 27% of all applicants were minorities. So there's something that bothers me about this 0.19, and is that it's not the number 0.27. We could say, well, on average, we hire 27% minorities. Sometimes it's higher, sometimes it's lower. So it would actually make more sense to assume that there's nothing scandalous going on, that on average we hire the same proportion of applicants as there are in the population. So I wouldn't put 0.1, I mean, if P represents the proportion of minorities hired, we would assume that it's the same as those that applied. It's a percent that applied. Now, notice that the way that this is written out is not numerically, though. We can use numbers to tell the story, but here we're using words to tell the story. And so we're going to use these words: a company is not discriminating. If we're not discriminating, that means it's the same thing as saying that the proportion that we hire is the same as the proportion of minorities that apply. And the alternate hypothesis is that the company is discriminating, which means that the proportion that are hired is actually less than 2.27 on average. So this is a one-tailed test, because they wouldn't sue if too many minorities were hired. And in this context, what would a type 1 error be? A type 1 error would be concluding that there's sufficient evidence that the company is discriminating against minorities when they are actually not discriminating. A type 2 error would be concluding that there's insufficient evidence that the company is discriminating against minorities when they actually are discriminating. So notice that describing type 1 and type 2 in context requires that we connect the ideas of type 1 and type 2 errors to the context of the problem. So the power of the test would be the probability that discrimination is detected when it actually is occurring. And part E, if the hypothesis is tested at the 5% level of significance instead of 1%, how will this affect the power of the test? And here is where it's best off on the side to draw two bell curves on two separate levels where you show alpha, beta, and power. Then just imagine what happens when this bar moves back and forth. Which way are they moving it? If it's tested at 5% instead of 1%, does that mean that this bar is being moved to the right or to the left? Okay, Moose, you pointed this way. You said it's being moved to the right. Well, that's correct, because if we're changing the significance level from 5%, which is alpha, down to 1%, that means we have to shrink down the area under this tail. Alpha shrinks, which is correct. That means we're moving to the right. So now you can see the dynamics of what happens. As alpha shrinks, beta grows, and power shrinks. So, whoops, okay, 5% instead of 1%. Ooh, hold on a second. If it's tested at 5% instead of 1%, that means it was at 1%. Now we're moving it up to 5%. So actually, in fact, Moose, you probably saw that before I did, that it actually should be moved to the left, correct? Okay, yeah. So if we were at 1% and we're changing it to 5%, that means we move the bar to the left. That enables alpha to grow from 1 to 5. Beta shrinks, power grows. So imagining the movement of this bar in the alpha beta power diagram will help you answer questions about power.
What do you mean by power?
Power is always 1 minus beta. Beta plus power is always equal to 1. And I mean, so that's what it is visually. Power defined verbally is the probability of correctly rejecting the null hypothesis. The algebraic representation of power is always 1 minus beta, because beta plus power always equals 1. Okay? And now they're asking a more nuanced question here on the bottom about part F. If the lawsuit is based on hiring 37 employees, how many was it at first? At first it was, you tell us. It says higher or lower than if we were based on 87 hires. Okay, so 37. So if we go to 87 hires, N is bigger. And you know how these standard deviation formulas work. Actually, all we have is an approximation. So standard error of p hat equals the hypothesized value. So we're going to assume that we're doing okay. We're going to assume that we're actually hiring 27%. That was our null hypothesis is 27%. So it's going to be 0.27 times 0.73 over 37. Compare that to standard error of calculated by taking the square root of 0.27 times 0.73 over 87. So, since there's a bigger number here in the denominator, this is going to be a smaller standard deviation. It's going to be narrower. And so they're asking about what power does. How is power affected by a bigger sample size? Well, what would a bigger sample size do to this curve right here? Would it make it more spread out or less spread out?
Less.
Yeah, if the standard deviation is smaller, this would be less spread out. So if you can imagine this curve suddenly being less spread out, what would that do to the area labeled power? Would it increase or decrease?
Increase.
Yeah, it would actually decrease, because if this gets, and I'll draw it for you, if this gets less spread out, then there's less, then beta shrinks. You can see the beta shrinking, which means power grows.
So it would increase.
So, yeah, it's lower when the lawsuit's based on 37 employees instead of 87. Lower sample size leads to less power. So, intuitively, that should make a lot of sense. Our decision-making system should get better with higher sample sizes. Bigger sample sizes means more power. You can see it graphically. So lower when the lawsuit's based on 37, higher when the lawsuit is based on 87. All right, let's go to the next page. This is the dropout problem. And I want to see if we have new material here, one tail, two tail. Yeah. Stats professor has observed that for several years, about 13% of the students who initially enroll the course withdraw before the end of the semester. salesman suggested if you try a statistics software package, it gets students more involved with computers, then fewer students will drop out. Let's let them work on computers. They'll want to stay in the course. So, software is expensive. The salesman offers to let the professor use it for a semester to see if the dropout rate goes down. So notice that the null hypothesis is that the software does nothing. Now, notice how that's expressed numerically. P, which I cry foul because here someone's trying to write down the letter P without attaching meaning to it with words. So we're going to let P represent what? Can someone give me the words we should attach or use to define P? I'll take a volunteer. What does P represent? Yeah, go ahead. Oh, yeah, yes, please.
Proportion of students who drop out.
So, thanks, Brittany. That's P represent the proportion of students who drop at semester. Good. And so, expressed verbally, we're saying that the dropout rate does not change after use of the software, or that it decreases. Yeah, there is one more thing here we're going to add verbally. Represent the proportion of students who drop out at semester when using the software. Okay. So, in the context, what would happen if the professor makes a type 1 error that's incorrectly rejecting the null hypothesis? That means he buys the software when the dropout rate has not actually decreased. And yeah, you can skip the word picture 13 words. They're not doing that. So I think, let me see, got on the bottom here, the type 2 error would be that the professor makes a type 2 error if he doesn't buy the software when the dropout rate actually has decreased. And the part of the test is the probability of buying the software when the dropout rate has actually decreased. So those are just some examples for you of how type 1 and type 2 show up in various contexts. I'd like you to take out your AB 80 sheet. AB 80, 5624, CD, donate your car today, 8, 2. So, on your AB 80 sheet, I'd like you to fill in row 2. And
Mr. Royce, can I see, sorry, can I see letter?
oh, do you just need to see that previous one?
Yeah, sorry.
Tell you what, I'll let you see that after class. For now, let's fill in row 2 of the AB 80 sheet. We're gonna look at the difference of two proportions. And this will be our lesson for tomorrow. But I want you to get this piece of it today. It's called the two proportion z-test. And we're going to try to build a p-trap, it's actually called a d-trap, D for difference, a trap for the difference between two proportions. That's putting the 6 in the AB 80, 56, 24. The test statistic is, and instead of p hat, it's p hat 1 minus p hat 2. The null hypothesis is that the difference between the proportions is 0. So it really is modeled after this. Instead of p hat, we have the difference of p hats. Instead of p0, we have 0. Now this word is pooled. And so tomorrow in our lesson, we're going to learn what a pooled proportion is. P hat pooled, Q hat pooled, times the quantity, 1 over n1 plus 1 over n2. Happily, this formula is on your green formula sheet, so this is one you will not have to memorize, but you will have to use it. So we're going to practice using that formula tomorrow. That's 1 over n1 plus 1 over n2. On the left half of row 2, your AB80 sheet, for building a D trap, which is also called a 2 proportion Z interval, that's where we're going to start tomorrow. We're going to fill in the givens here for the 2 proportion Z interval. So, I would strongly recommend that tonight you work on the mega packet in preparation. The test will not be tomorrow. I'm going to, we'll take the test a week. It'll be either block day or Friday of this week. But test will be this week. You are dismissed.